let me take a couple of minutes to introduce Andrew Richards. Andrew is the CEO and founder of Codeplay software. He's going to be telling us today about programming techniques for implementing inference software efficiently. He founded Codeplay in 2002. It was the first C++ compiler for GPUs, and since then the team has grown to 60 expert engineers, focusing on tools and products to enable processing in specialized processors. Most recently, he has been connecting AI to silicon through open standards. So tell us a couple of things about Codeplay.
So we were actually founded to put compilers on graphics processors. I was originally a video game developer.
Oh.
And I could see that graphics processors were becoming incredibly powerful, and you could maybe use them for other things or more complicated things. So we were actually the first people to put C and C++ onto a graphics processor about, what, 18 years ago now? And I assumed that it was for video games. I assumed that everyone would want to be able to use this stuff to do more interesting things in video games. But actually, one of our earliest users actually did stuff for machine vision. He did eye tracking. And they did this 3D display that would track your eyes, and so you could see in 3D as you move your eyes around. I didn't spot that that was the main use for these things, but over the years, people would occasionally do little AI things with that. Gosh, that's surprising about it.
Very important nowadays. Well, I'll let you get started. So please,
okay,
let's welcome Andrew.
Thank you. So this talk is going to be about how you build inference engines, maybe even some training stuff as well. And there are a lot of different options about how you were to build software to do all sorts of artificial intelligence and machine vision, like the previous talk was all about SLAM, using some, maybe I shouldn't say traditional machine vision techniques, but it doesn't use deep learning for those techniques. But we do find that people integrate all of these different technologies together. And there are a bewildering array of options for how you build these systems. I'm going to focus much more on how to build your own systems, but I'm still going to show some of the options about how you build the systems and what things are out there. But our background as a company is compiler tools, so I'm going to focus a bit more on that. But if you've got your neural network, the options that you've got is you could use an existing framework like TensorFlow or Caffe. You could use some kind of hardware-specific inference engine. So there's many companies here who design their own chips. And what they do is they have their own hardware-specific inference engine. So you could take your network out of something big like TensorFlow or Caffe, where you've trained it and put it into an inference engine. You could use some really hardcore low-level programming models, like I might have done in the early days as a video game developer. It got a bit more complicated now, but you might want to go all the way down to getting assembly language or just device-specific programming if you want to eke out the maximum performance. Or you could write your own inference engine using some accelerator programming model. You might use CUDA. A lot of people use CUDA, but Codeplay as a company is more interested in open standards like OpenCL and SYCL or something vendor-specific. But how do you make those choices? And I'm going to talk in a bit of detail about some of those different options. Bit more about Codeplay. We're based in Edinburgh, in Scotland. Right outside our window is a sheer rock face and then a castle on top. So we're definitely quite a Scottish company, despite, as I said, I'm actually from England. And you brought the weather for us, or we've brought the weather from Scotland here to California, unfortunately. Sorry about that. We build GPU compilers for semiconductor companies. Actually, they're often not GPUs anymore. They're often designed today for specific vision processors or AI processors. And we're working a lot now on making AI acceleration safe for automotive applications. So although we started designing video games, people literally want to drive cars using our technology. But I chaired the SYCL group when we defined that standard, and also the HSA Software Foundation, because we do a lot of open standard stuff. So let's try and understand the problem at first. Why is there a problem? So this is a slide that based on looking at the raw performance figures of various different processors. And you'll see what I've stuck at the top there is a target that Google set a few years ago. Their self-driving car team set a target of, I think it was 50 teraflops. And if you look at when different kind of technologies are going to get there, the desktop GPUs and smartphone GPUs actually get there at the same time, which violates the laws of physics and shows you how much smartphones are actually fiddling some of the figures. But you can still see that GPUs actually get to that performance level in a reasonable amount of time, whereas CPUs would take 5 to 10 years after that. So it simply isn't practical to be able to use CPUs to get to very high performance levels. We've got to look at GPUs or GPU-like things. So when you're looking at what it is you want to build, there is a few questions that you have to ask. So I've already brought up one, which is safety. Automotive and medical applications need safety, so you need to be able to validate the software. So that's actually one of the toughest things that you've got to think about. Now, networks, we don't understand how networks work. Maybe somebody here is going to claim they do, but I think most people are honest. We don't really understand how neural networks work, so they're hard to qualify beyond some statistical testing. But actually, the software has issues itself. So for example, the AI processors like graphics processors tend to throttle. That is, slow down when they get hot. And that's quite an important thing if you think that your car processor might be having to detect a pedestrian. Then there's a whole range of tools that you might expect. You might normally expect source line debuggers and stuff like that. That's actually quite hard to deliver on parallel processors. We do it, but it's hard to do. And also you've got to ask, are you doing any unusual AI operations? So if you use an existing piece of software, are the operations that you need supported by your network? And if not, can you add them? And that's quite a fundamental question. And so sometimes you have the problem of, has this network been designed, or the inference engine been designed a way to add custom nodes? And some inference engines only target one AI processor, so the question is, can you switch different processors, or are you using something very proprietary? These are the questions that you've got to ask. So on the left, I've got a typical network. I think it's AlexNet. And on the right, so you might want to run in your existing framework. So you might just want to run in TensorFlow or Caffe. And the advantage of that, it lets you do the training and inference on the same code. But, you know, it's a big application. It might be small to shrink it down to run on a device. You might export your inference framework onto something like TensorFlow or some TensorFlow Lite, Android NN. There's a whole load of small systems that you might do. Or you might, and this is the cool stuff that we as a compiler company are interested in, you might actually want to hard compile your network into code. So you might take a neural network on the left and take a compiler that actually converts it into device-specific code, which is quite an interesting thing. Or you might want to write all of your own engine using existing libraries. So for example, TensorFlow uses this Eigen library. There's this ARM compute library, which is now open source, that allows you to build these things for ARM devices. It is more work, but it gives you the greatest flexibility. So let's start at running in a framework. So this is comparing all of the different ways that you might run TensorFlow. So what we've got is the number of TensorFlow operations that are supported on the CPU, which is at 873, and then the number of operations supported by CUDA, which is 360. So inside TensorFlow, the NVIDIA GPUs with CUDA can accelerate 360 of those operations. Now, the reason that a lot of those operations aren't accelerated on the GPU is because they're things like loading from a file, right? So it's irrelevant. You don't want to, you can't accelerate that on a GPU, but there's a lot of operations. And then what we've done is we've worked in the open source repositories and in a standards body with a SYCL standard to get 269 of those operations supported in almost the same source code. I'm going to talk a little bit about how we've done that. But if you have a look at the inference engines, you can see that the number of operations they support is hugely smaller. So the kind of once you go down to something specific, the numbers of operators are much smaller. So you've got to ask the question, is that going to be good enough for you? And actually, for a lot of networks, it is. Those 29 operators are often very good, but if you're doing something special or unique, it might not be. So let's talk about exporting from TensorFlow or Caffe into some other network. I've spotted that there's two main competing standards. There's NNEF and ONNX. If only they could be integrated into one standard, but there you go. There's that famous cartoon, isn't there, about we've got new standards. But anyway, it is really good that we've got, well, even though they only explicitly support ARM, CPU, and Mali. CEVA have one, Qualcomm have one, Huawei have one. NVIDIA has TensorRT, which is quite interesting because that's more of a compiler system. So I'm going to come back to that. And Intel has one. So these are ones that are specific for each processor. But of course, if you use that, then you're locked to that processor. But maybe if it's a shared format, you don't need to worry about that. So the cool stuff is compiling a network to optimize code. So TensorRT does this from NVIDIA. XLA does this in Google. So I'm going to explain why. This is some analysis we did a while ago. I still show this because I think it is quite important to understand why this is working. So what we've got is this graph is showing time. So the higher bars are slower, the lower bars are faster. And what we've done is we've taken three very simple operators in machine vision, and we've run them in OpenCV, which is hand-coded OpenCL code. And the blue bars are the kernel time, so that's executing on the GPU. And the yellow bars are overhead. So actually that's copying to and from the device and just setting things up and enqueuing work. So the first thing we do on the left is we run the three operators completely separately. So you can see it runs on the GPU, then it's overhead, runs on the GPU, then some overhead. Right? Why do that? Why not say we'll run three operators together and then do the overhead once? So that's what the next one along does. We say to OpenCV, run them all together. Now, OpenCV is not really a graph programming model, so what it can't do is combine those nodes together. So it just runs them one after the other. So you can see all the kernels are run one after the other. But the overhead is less. So it's faster doing it that way. Now, Halide is an open source library. It does an interesting thing. It can process those nodes and fuse them together. Now, that means its overhead is much greater than OpenCV. But look what happens when we give Halide those three nodes together. What it does is it combines them into just one kernel. So you can see the three combined is only very slightly slower than just one on its own. And the overhead is still larger than OpenCV, but the result is actually faster than OpenCV. So by fusing operations together into one kernel, we make them go much faster. And that's basically because these operations are bandwidth bound, not compute bound. So we keep all of the data on the chip. Now, with the SYCL standard, we can use C++. We can use C++ to do the fusion. So you can see that SYCL gives you slightly greater overhead on top of OpenCL than OpenCV, but the kernels are actually the same speed. But C++ allows you to do kernel fusion at compile time in a way that I'm not going to go into here, but it's very widely used, this technique. It's called a C++ embedded domain-specific language. And by doing this at compile time, we can actually get much faster performance than all of the other options. Now, it's not a feature of just SYCL. This is a feature of C++. By using C++, you'd get the same thing with CUDA. You'd get the same thing with a whole other programming models that give you single source C++. It allows you to do the fusion at compile time. And this is used inside TensorFlow, inside the Eigen library. So, inside TensorFlow, what we actually see is they have the Eigen library, which is compile time, but they also have this cool thing called XLA, which is a compiler that runs at compile time. And there's another open system called TVM, so you can look up that as well. What they do is they take an entire graph, they convert it to a very high level format, and then they break it down. And one of the things that I work very hard on inside the Kronos group is to define the SPEAR and SPEAR-V standards, which actually opens up the compiler stack of accelerators inside OpenCL and now Vulkan. And so it's actually much easier to build these systems because there is a standard intermediate representation that allows you to build a compiler on top. And we've worked on lots of projects. We did the CLSPV project, but there's lots of projects all based around LLVM that allow you to use all of these standard formats. So a lot of work has been done to enable you to build these compilers and be able to combine these things together. Another thing that you can do is at runtime, you can take a whole graph, and then you can fuse it and optimize it together without using a compiler. And what you do is you provide pre-fused nodes. And then, of course, compile time graphs is what I showed before. So Halide or C++, which is in the Eigen library used by TensorFlow, you just have a C++ compiler, and SYCL enables you to do that. The advantage of this is it's compile time, and that allows you to verify the code, pre-build the code for your device. It's good for embedded systems. So, if you want to write your own inference engine, what do you need to do? So, you need to think about the acceleration because you want to keep almost all of the processing on the accelerators, but you also need to think a lot about data management, and this is a huge issue with these accelerators. You can't just rely on the accelerators just having pointers to memory anywhere. Data management, you know when I was showing that graph and the overhead was much larger than the kernels? Data management uses up more of your time than processing in a lot of these systems. So think about data management more than all of the other acceleration issues. You then need to adapt the algorithm to your hardware. I'm going to show you some numbers. I'm going to show you some actual graphs that we've taken from real devices in the next few slides. But the algorithm needs to change according to the processor. You also need to make use of fixed function hardware. Increasingly, you will see that the accelerators today have fixed function hardware for specific deep learning tasks. And so you want to be able to make sure that you use that fixed function hardware for all of the things that that hardware can do, whilst also being able to efficiently use the programmable nodes. And of course, the last thing is you want to be able to maintain it over a long period of time, which is something that we've worked very hard on by defining standards. So if we break it down into a smaller set of problems, there are 4 real issues that we look at. One is convolutions. There's lots of convolutions. It's hugely important for performance of deep learning. And the convolutions are weird. Right? There's lots of variations. Matrix multiply. There may not be that many matrix multipliers. They call them fully connected layers in deep learning, but actually, as we've seen in previous talks today, a lot of convolutions use matrix multiply operations underneath. So the matrix multiply operations are really hard to do. They're highly optimized. If you look at the CUDA ones in cuDNN and cuBLAS, they are extremely highly optimized. It's very, very difficult to hit that level of performance unless you put a lot of work into it. So be prepared for that being the major issue. Then you have component-wise operations like adding and subtracting, multiplying vectors together or tensors. It's highly bandwidth bound, but there are a lot of different operations that act like this. So you need to be able to develop them very quickly, but from an optimization point of view, it's only fusion that really matters. And the last thing is reductions and partial reductions, things like max pooling. Reduction algorithms vary by processor, and things like Eigen allow you to create a generic reduction algorithm for each processor, and all of your different reductions just use that algorithm. But it's, you want to be able to genericize that as much as possible, if that's a word. So hang on, I'm going to show you some numbers. It's not very easy to understand these slides at first, but hopefully they'll start to make sense. What we've done here is we've got 5 different convolution algorithms. So we've got 4 direct. Direct is kind of trivial code, right? You just for loop over the things. Direct tiled, which is quite a simplified tiled operation. IM to col, where you convert your convolution into a matrix, do the convolution via a matrix multiply and then convert it back. Some convolutions aren't really convolutions, they're matrix multiplies. I don't know why you just call them matrix multiplies, but you call them one-by-one convolutions. And then Winograd technique, which is this sneaky technique which does complicated matrix multiplies. So what we've done is we've run these different algorithms on different sizes and shapes of convolution that you see in deep learning, and then we've run them on 2 devices, the AMD GPU and the ARM Mali GPU. And you can see for different sizes and shapes of convolution, the variation in performance is quite large. So I think we're only showing about up to 3 times. I think I'm hiding a few extreme ones. If we go to the next one, yeah, in the training case, it gets much more extreme. So these are the training ones, and these are the inference ones. So the convolutions are slightly different in the case of training and inference. But you can see that the algorithm that is fastest varies, and it varies in a way that's very different by device. So you need all of the algorithms. A typical neural network will use multiple different convolutions. So each one may need different algorithms. We see similar results with matrix multipliers. It's not quite so much algorithmic, but the way you tile things and stuff is quite complicated. So this means it's something that you've got to think about. You can't just write one convolution, even for one neural network. Certainly not if you want to run it on different devices. So what we're now doing is running benchmarks and studying heuristics to work out which is the right algorithm, which case for which device, and then adapting according to that device. This work is going to be open sourced in a project called SYCL-DNN, which will use the SYCL standard, but give you lots of convolutions that will adapt to different devices. So this is what it looks for the component-wise and reduction operations inside Eigen using SYCL. And what have we got here? We've got on the left, we've got it on the ARM Mali GPU on the High-Key 960 board, which is just a board that you can buy from Amazon. We can run TensorFlow on that. And what we've done is we've compared the A53 CPU, which is the little low-power CPU. There's 4 of them. The A73 CPU, which is much larger, it's what ARM called the big and little CPUs. They're using Neon, so they're vectorized, and they're using all 4 cores, and then using the Mali GPU. And what this is on the left is it's showing all of the Eigen operations, which are component-wise, they're partial reductions, and I think there are some of the tensor contractions in there as well. But tensor contraction is a kind of posh name for matrix multiply, but kind of multi-dimensional. So you can see we get quite, in some cases, we get really quite large performance boosts on relatively trivial algorithms, but the advantage of the Eigen library is we can build those up into much more complicated operations. They're all generic operations. And on the right, you can see we can compare CUDA with an equivalent AMD, or 2 equivalent AMD GPUs. And you can see sometimes the AMD GPUs have much, much higher bandwidth. And so therefore, they're able to achieve twice the performance as NVIDIA GPUs. But we seem to get AMD GPUs getting much lower performance than the NVIDIA GPUs on random memory accessors. So you can see the kind of design decisions in the hardware make big, big performance differences, much bigger than you might expect to see on a CPU. They make big, big performance differences to how things operate in the wild. This is all open source, so you can have a look at that and you can download it and try it out. And some people, actually, we've seen build their own inference engines using the Eigen library because Eigen creates so much. So rather than taking TensorFlow, they take the Eigen library, which is part of TensorFlow, and build up all their own operations within it. So this is showing the difference that we get currently with the open source SYCL matrix multiply operations across a range of sizes compared with cuBLAS. And you can see on very large sizes, it's possible to get pretty close to cuBLAS performance on, this is AMD GPUs. But as the sizes get smaller, it's much, much harder to hit those performance levels. And we've not been able to manage this yet with our open source SYCL BLAS. But you can see for the larger sizes, we can get very, very close to CUDA performance. So this is one of the things that you've got to think about, and this is some of the things that we've learned. So we've created this SYCL BLAS library that adapts the algorithms to different GPUs, just like the SYCL-DNN that adapts to convolutions. But you can see that you really need to do a lot of work to be able to hit the same level of performance that NVIDIA has done with CUDA if you want to be able to run it on lots of devices. And that's because you need to be able to adapt the algorithm to different shapes and sizes. So the algorithm that's really good at very large sizes is not necessarily the right algorithm for very small sizes. And this is something that we're still working on to be able to get those performance levels up. But again, this is all open source, so you can try this out, and if you can work out how to speed up some of the smaller sizes. I saw a presentation last week on CL Blast, which has some of the same problems that they're having to adapt algorithms to smaller sizes of matrix. One of the solutions is to be able to batch up lots of matrix multipliers together. So, performance conclusions. Convolutions, you need to vary the algorithm by convolution shape. Matrix multiply, you need to vary the algorithm by matrix shape. It's very hard to beat cuBLAS. You need a lot of highly optimized kernels. And they need to be different for each device, unfortunately. So this is something that we need to do more work on. Component-wise operations and reductions, there's lots of them. There's hundreds of them that you need. As long as you've got something that enables kernel fusion, and C++ enables this, then you can actually do that. We've got this other library called Vision CPP. It's an open source library that we developed. This C++ technique that we use is very common. We come from a games industry background where it's very widely used. It's very hard to understand at first. Vision CPP is open source. It's on GitHub. It makes it much easier to understand. It's much simplified. It's a much simpler system. And you really need to minimize CPU synchronization. That's one of the problems why we're having problems on small sizes of matrix. You want to get rid of the CPU synchronization. It kills you on lots of small size operations. So this is our approach. We use LLVM at the bottom. That's the standard compiler for all of this stuff. I think pretty much everyone uses that. We then use OpenCL Spear, which then allows you to build other compilers on top. And in some cases, we use Spear V, which is the newer one, which is better. We then use SYCL and OpenCL C. SYCL is our C++ model. C is our OpenCL C model. That's pretty standard. And then at the top, we enable TensorFlow via SYCL, and we enable OpenCV and various other things via OpenCL. So this is what we've chosen as our layers, and we have chosen these as standards. That's why we've chosen these things, because they seem to be the most widely adopted standards that give you what you need. And here is some links to some of the things that I've talked about today. So hopefully, I don't think I've answered all your questions about how to do this, but I've linked you, I've given a good overview so that you can start to ask the question, how do I build this up? And look at all of the existing resources out there so you don't reinvent the wheel. And that's my talk.
Thank you very much, Andrew, for a very interesting talk. So just to remind you, there are 2 microphones in the aisles. If you have any questions, you can please come up to the mics and ask your question.
Hi, I'm Gary with Intel. I noticed on your slide, I think it was 19 or 20, where you had some circular plots on AMD Mali and, ARM Mali and AMD. And you were showing like 1x, 2x, 3x, and 4x. What are you comparing? Where does that 1x, 2x, and 3x, and 4x comparison of performance?
I mean, the problem is the size of the convolutions. You can only compare it relatively. So the 1x there, I've used a baseline of IM2col in both cases. So IM2col is the one where you convert a convolution into a matrix multiply, and it works in almost all situations, and it works with different strides and stuff like that. So really, you've got to look at them totally as relative. This is the relative performance of each algorithm compared with other algorithms.
So each line, whether it's blue or yellow or orange, represents a particular function, and the relative to the... It's
an algorithm. So they're all doing the same operation. Yeah. I know it's a confusing graph. It does make sense once you've got your head around it, but each color is a different algorithm doing the same operation. And around the circle is doing the different sizes and shapes of convolutions.
So you can just see the variation of the performance as you go among different algorithms. I see. Thank
you. So as they the ones that are further out are faster, so you can see which algorithm is best. So when the yellow is further out, you should use that algorithm for that size. Yeah.
Thank you so much.
But do you have a way to have a single number that tells you everything, like an integration of the area within that? Is this a single number?
You could, but what you don't want is what this graph is telling you is you don't want to only have one algorithm.
Indeed. Right.
So what we do from these graphs is we create a heuristic that says for this processor, this is how you calculate what the correct algorithm is for a particular size of convolution.
Right.
And if you only have one algorithm, you'll be killed on performance compared with somebody who has really hand optimized that.
Yeah, I like that. Please.
Interesting talk. Sort of a couple of questions. Just to make sure, so you mentioned LLVM underneath, but it really sounds like you're doing more library stuff and stuff up above rather than sort of compiling directly. Just wanted to make sure if I understood that correctly or incorrectly. And sort of second question, follow on, I'll get in there and then sit down. So you focused on GPUs. Have you looked at sort of other devices like DSPs and FPGA and stuff like that for doing the same type of approach?
So the first answer is actually we as a company are a compiler company. So some of this work is library work, but to get rid of to try and explain the confusion, What OpenCL Spear and SpearV allows you to do is have 2 layers of compiler. So an OpenCL implementation from Intel or AMD or ARM will take in the Spear or SpearV code and compile it down to the actual GPU that you've got in your system. And then what we do is we provide a SYCL compiler. SYCL is basically C++ that compiles from C++ down to that Spear format. And actually, a lot of the tools to do that are all open source, so you can do it yourself. So I saw a talk last week where they took the D language and compiled from D down to LLVM IR that went to Spear and then went to the device. So when we talk about SYCL, that is a compiler flow, but we're also doing libraries as well. So some of the work here is using SYCL, but it is a convolution library, which is a library. And then you have the second question. I can't remember the second question, but sorry, after you said that. No, it was an interesting question, which is why I'm forcing you to come back. DSPs and FPGAs, yes. Good question. There's a workshop. It's a Synopsys-sponsored workshop on Thursday here, where I'm talking specifically about some of the work we do on DSPs. We do actually do stuff on other kinds of processors. So we're working with Renesas on their RCAR platform, which is a driver assistance system. I can't show any figures for that yet, but that's a processor which isn't a GPU. It is specifically designed for vision. And we have some other customers where we're doing vision DSPs. And in my view, I think that the OpenCL model does map to DSPs that have very wide vector instructions, which is quite common today. If you take a DSP and turn it into a vision processor, you tend to have these very wide vector instructions. OpenCL vectorization does actually map very well to that. It's a bit weird at first. One of the things that we do have to do is manual DMA, which is something that we as a company had to do with the PlayStation 3 hardware and actually PlayStation 2 hardware, so we have quite a lot of experience of it. GPUs, you don't have to manually DMA stuff in, whereas DSPs you do. So GPUs just hide the latency by running huge numbers of threads. On a DSP-type device, you have to control that memory much more manually. Now, I think that the SYCL approach and the kind of SYCL DNN approach that we've got here will allow you to do it. I haven't gone into the details yet. We've done it before. I haven't gone into the details yet because no one's publicly enabled any of these systems to work. But when they do, we'll show you how to use some of these techniques to get DSPs to work. And we'll see if they really are more power efficient for these kind of tasks.
Well, we're running out of time, so thank you very much, Andrew.
Thank you.